Good afternoon, everyone. Am I audible and this is screen visible?
Good afternoon, sir.
Is screen visible?
No, sir.
Wait a second. Okay, good afternoon once again, everyone. Welcome to Design of Reinforced Concrete Structures. It's a week three live session, and today we will be doing directly to the problem solving session without discussing any theory part. In the third week, you have studied limit state design in Flagger, and both analysis and design is going on in week three lectures. So we will be discussing the problems related to that topic only. So let me start. So I have here given the basic formulas. These are the important formulas that we will be using in solving our questions today. The first is a strain and the tension reinforcement. From this diagram, we can see that here is a cross section of a beam having effective depth. I'm sorry, made it wrong here. Its effective depth D and width B. It is the strain profile here, and this is the stress block diagram here. And here this EST is the strain at the centroid of the steel. EST star is 0.87 Fi by ES plus 0.00.02. So you all be familiar with this formula from the lectures that you have studied. It's actually 0.002. It is the strain at the centroid of the steel, and the strain in the steel should be at least greater than or equal to epsilon st. This ensures that our section is under reinforced and the yielding of the steel has occurred. This is the stress block. 0.447 FCK is the stress that comes there, and 0.87 FI is the stress in the steel. It is all because of the factor of the safety 1.15 for steel and 1.5 for the concrete. And this is the our lever arm ZAD. CW is the CU is the total compressive force acting on our section, and 0.87 FIAST is the total tensile force acting on the steel bars. Limiting depth of the neutral axis. These formulas all can be derived from this. This is the basic diagram that you have to recall every time. You should be able to draw it at any instant whenever you have to solve any problem related to analysis. Because all these upcoming formulas are just the derivation from this basic diagram. This xu by d, you can deduce it from the previous diagram. This is given by this 0.0035 divided by 0.0035 plus est. And it is only valid when est is greater than or equal to epsilon st star. I already told you why it should be greater than. That it ensures that our steel has at least yielded. There is the yielding of steel, that the tension is occurring in our steel bars. And it has an upper limit only when EST becomes equal to EST star. There we call that the depth of the neutral axis has reached its maximum value. After that, the section becomes over reinforced. XU max by D is given by this formula. And the compression force that comes on our beam section is Cu. It is given by 0.362 FCK BXU. FCK is grade of concrete, B is the width, and XU is the depth of the neutral axis. And X bar, this compressive force actually it is like this. It's like this. This compressive force acts at some distance here, because we all know below neutral axis it is tension, and above neutral axis compression. This total compressive force on our beam section acts at some distance from the topmost fiber. That's x bar. It is 0.041 0.416 XU. That's given here. Tension force that I already TU is called FST AST already showed here. TU is equal to 0.87 FY AST. Here this FST is 0.87 FY. We take the yield strength of the steel and divide it by the factor of safety 1.15. That comes out to be 0.87. These formulas are valid up to XU less or equal to XU max. Depth of the neutral axis, we can get this the depth of the neutral axis by this. You would have already studied in the lectures that we equate equilibrium equation Cu equals Tu. From Cu, you have the formula 0.36 FCK BXU, and Tu is this. When you solve it for XU, you get this formula. This is valid up to XU less than XU max. Every formula is valid up to XU max less than XU max. When you have to solve it beyond XU is greater than XU max, there we adopt a method known as strain compatibility method that we also discuss in the coming couple of minutes. Then there comes the ultimate moment of resistance. This is the ultimate moment of resistance is the bending moment that our section is capable to resist. Maximum bending moment that it will resist is we already calculated the forces Cu, or we calculated Tu. When this is Cu, this is Tu. If we multiply it by a lever arm, that's the distance between these two couples, the compression force and tension force, we will get the moment of resistance of our given section. Look, you can see that here it is actually the Cu term, and I have already only multiplied it with the lever arm distance Z, d minus 0.416 XU, valid up to XU less than XU max. And same is FST AST. FST AST is TU and multiplied by lever arm. You can remember these formulas like this way. It is force multiplied by the lever arm is equal to moment. This is the simplest way you can remember these lengthy formulas. So before the section becomes over reinforced, there is a limit of this moment of resistance. That is, if the neutral axis depth is up to the maximum neutral axis depth, we call this moment of the resistance as the limiting moment of resistance. Beyond it, after that, it will become over reinforced section. The code has given a expression for this mu limiting is like this. When you substitute xu here as xu here as xu limiting, we will get this formula. Mu limiting as same, it is the same formula, but there is some rearrangement done here. Mu limiting, it is divided, whole equation is divided by fck bd square. Actually this fck mu limiting divided by fck bd square, it becomes a dimensionless parameter k, which is given by 0.36 times this term. Actually, this parameter only depends upon the grade of the steel, and it is independent of the anything effective depth, or it is independent of the XUmax is already there, but it's independent of the grade of concrete as well. You can see from this formula, it only depends upon the grade of the steel. Same like mu limiting, we have a limiting percentage of tensile steel. It is given by 41.61 FCK by F by XUmax by D. And this table I have kept for the strain compatibility method. So our formula is like this. We are given a beam section of it's actually the problem from the previous week in which we solved it with WSM method. Here we will be doing the analysis of the same beam section with using limit states method. So in this, from the previous problem, we have the breadth of the beam as with 300 mm, and we have effective depth D as 550 mm. And I have already written here this grade of steel that we have to use is 415 megapascal, and grade of concrete is 20 megapascal, and AST here AST is 1963. From the previous last week's problem, you can see that there were some 425 bars like that. So first, how do we analyze? For this, we have to calculate. First thing, we have to calculate neutral axis depth. This is the first point. Second, we have to calculate Second, we have to check, is XU less than XU max? If so, if this condition is okay, then we can proceed further. But if this is not true, what is the third step we have to do? We have to calculate, we will, before starting the neutral axis depth calculation, we will calculate XU max at first hand. Firstly, we will calculate this and then calculate XU. We then check XU is less than XU max, then it's okay. We can further proceed to the calculation. But if it's not so, XU if greater than XU max, we have to perform a cycle of iterations to get the actual depth of the neutral axis actual. That we do by strain compatibility method. We do that by strain compatibility method. That we will be also doing. After that, when we get the from this strain compatibility method, we get the actual depth of the neutral axis. We proceed further. So for XU max, first step is to calculate XU max. XU max. We have it's a table given in code. We have there it is given XU max by effective depth D ratios. It's like this. We have given different ratios like this. It's XU max, and here it's for different grades of steel. Grades of steel. It's like this. For example, if we have Fe 250 grade steel, our XU max by D ratio would have been 0.5313. Fe 415, it would have been 0.4791. If it is Fe 500, it will be 0.456. Because actually we can see that it only depends on the XU max by D ratio, only depends upon the from this equation. XU max by D, this equation, XU max by D only depends upon the grade of the steel Fi. It's independent of all the quantities, section, dimensions, or the grade of concrete. So when we plug in here Fy 415, we will get this ratio. That is this ratio shown here. This Fe415, Fe415.4791. So we will write XU max by D as 0.4791. When we put the value of D as 550, we get XU max as 0.4791 multiplied by 550. It will be equal to 263.5 mm. That's the first step we have to do. We got the value of maximum neutral axis depth. This is the value. If our neutral axis goes beyond it, our section will turn into an over reinforced section. If the XU is less than this, it will be this. So we have to go for XU. Now we have to calculate neutral axis depth. Now XU formula is already given as this one. We have to take this formula. XU 0.87 FIAST. 0.87 FYAST divided by 0.362 FCKB. We have all the values when we plug them. 0.87 Fy is 415, AST is 1963 mm square, 0.362, FCK is 20, and B is 300. We can also check the consistency of the units as well. It's better to write the units everywhere. We can see that here it was megapascal, it got cancelled with megapascal. 0.362 was constant, it was also constant here, it was mm square here, and it was 300 mm here. Mm square goes, it remains only mm. When we calculate it, it comes out to be 326.3 XU. Our XU came like this. Okay. Now we have to check. Check. XU is 326.3, but XU max is 263.5. Clearly, our XU is greater than XU max. So we have to calculate the actual depth, but which we will do by strain compatibility method. What is the you would have asked the question here? What is the meaning of this? XU is greater than XU max. Actually, if we see our concrete section, if it was XU max, when we calculated from that C equals T formula, our depth of neutral axis came like this. XU came like this. It means that our steel has not yielded. That's whole this is the compression area. This is the section of the this is area of the section of beam is active in taking the compression, and this only portion is in tension. But this is not true. It has gone below the XU max. So it means that our steel has not yielded, but we have made the assumption already before there that the strain should be at least greater than this. Strain should be at least greater. The EST should be greater than EST star. So as to ensure strain should be yielded. So we have to make use of compatibility to ensure that strain is at least greater than strain at the centroid of the steel bars is greater than EST star. For that, we will perform iterations to get the actual depth of the neutral axis. So we will use first cycle of iteration. In first cycle, we will make assumption first. We will assume XU approximately as an average value of what we got XU, what is our XU max, and what we got from the equation C equals T. That is plus XU divided by 2. We will assume that. It is XU max was our 264, I think approximately. It was 260.5, it's 263, 264. Plus XU is 326.3 divided by 2. When we calculate this comes out to be 295 mm XU. Now, from this depth of the neutral axis, we have to see what is the strain coming in the steel. There is a formula for strain at the centroid of steel, and relating it to the neutral axis depth as EST is equal to 0.0035. It's D by XU minus 1. These all formulas you can get it from this basic figure. This is you have similar triangles, you have to evaluate just this side by this side. This is XU, this is D minus XU. When you use the property of the similar triangles, we can get this formula. So when we calculate this 0.0035, D is 550 divided by 295 minus 1. This comes out to be 0.00303. Now this strain EST, correspondingly we have to use stress strain. We have to use the stress strain curve of Fe415. Fe415. We have to use that Fe415 curve. We have to see where this 0.003 EST lies, and correspondingly we have to get our strain there. We have to get sigma there. We can do it from this table. Fe415 and our strain lies 0.00303. 0.00303. 0.00303. 0.00303. We can see that our strain lines between these two values. these two values. Our strain will lie anywhere between 351.8, 360.9. So interpolating our stress here, we have to use interpolation. FST will be equal to, I have to go to back table. First value 351.8, first value it will be plus, it will be the difference of the values 360.9 minus 351.8 into, we have the difference of the strains. We have to find it at 0.00303. We have 0.00303 303 minus, it is subtraction of the first value, 0.00276, 0.00276 divided by, it is a final value 0.00308 minus same value 0.00276. When we calculate this, FST is equal to 354.2 megapascal. You have to use the interpolation formula. For example, this is strain. We have epsilon 1, we have epsilon 2, we have stress, sigma 1, we have sigma 2. These all are known values. We have another value epsilon. On epsilon we have to find the stress sigma. We can get it by sigma will be, it will be, if you do the interpolation formula, sigma will be initial value sigma 1 plus difference of the stress values sigma 2 minus sigma 1 multiplied by the strain value, where you have to find epsilon minus initial strain value epsilon 1 divided by final strain value epsilon 2 minus initial strain value epsilon 1. This formula you can directly get it. So FST we got it 354.2 megapascal. So we can directly calculate our XU depth as equating now CU equals TU. Here in TU we were initially using 0.87 FY. That was something 0.87 into 415. We will calculate this 0.87 into 415. This comes out to be 361. 361.05. It means we were using the basic for stress in the steel as 0.87, but actually the stress in the steel, now when we assume that neutral axis depth, it comes out to be 354.2. That's below the yield point. So we are correcting the stresses, and up to that point we will get the true depth of the neutral axis. So when we equate this equation, we will get XU equal to FST AST divided by 0.362 FCKB. When you substitute all these values here, we get XU as 320.1 mm. 3 point cycle first. This is cycle first 320.1 mm. What we assumed, it was 295. So there is a difference. So we have to do iteration again using now this value. Cycle second. We will assume XU now. This 295 value plus what we got. Average of these. 320.1 plus 295 by 2. Taking the average of these two values, get 308 mm. 308 mm. Similarly, for 308 mm, I calculating the strain in the steel from this formula. Epsilon ST is equal to 0.0035 d by XU minus 1. Plugging all the values, we get the value of strain at the centroid of steel as 0.00275. Look for this strain value in the table. 0.00275. 0.00275. 0.00275 is sitting here. So the corresponding stress will be sitting here. Doing the interpolation formula like the same way, we get the value of FST as 351.5 megapascal. Look, it's coming down from what we assumed initially, 361.05 megapascal. So now this cycle second assumption of the neutral axis depth reduced the stress in the steel as 351.5 megapascal. So using the equilibrium formula again, Cu equals Tu, we get the value of Xu as, we have same FST as T.362 FCK BXU. If you plug in all the values, we will get the value now we are 317.7 mm XU. What we assumed XU 308, and what we got XU as 317.7. So we are converging to a solution of XU. Here is differences still are, but we will do one iteration more to see whether our solution converges or not. Cycle cycle 03. Now what we have to assume XU as? We will assume XU as value we got and we assumed 308 plus 317.7. 308 plus 317.7 by 2. We get 313 mm. Calculating the strain in the similar fashion, epsilon st we will get 0.0035 550 divided by 313 minus 1. We get the strain 0.00265. Look for this strain in the table, 0.00265. 0.00265. It's also staying here in between these two values, so stress will be like here. Interpolating the stress, we will get FST as, I showed in the first cycle how to interpolate the stress from the table, as 349.0 megapascal. So using the formula Cu equals Tu, we get Xu as FST times AST divided by 0.362. 0.362 FCKB. Plugging all the values, we will get the value as 315.4. So the neutral axis depth we got 315.4 mm and the assumed 3113. These are very close to each other, so we reach it at the closure of this iteration cycles as our solution converged XU at 315.4 mm. In this way, you have to calculate the depth of the neutral axis. If the depth, initially the depth from Cu equals Tu by considering the stress in the steel as 0.87 Fy comes that neutral axis depth comes greater than the depth of the maximum depth of the neutral axis. You have to perform a cycle of iterations to get the actual depth of the neutral axis Xu as 315.4 mm. So this is our neutral axis depth. Now we have to calculate different things. First thing we will calculate ultimate moment of resistance. Ultimate moment of resistance, I have written the formula already. MUR is equal to CU force divided by lever arm LA. CU force is already 0.362 FCK XU. XU times lever arm is D minus 0.416 XU. Just like this, no? CU acts at like this, and our T will act at the centroid of the steel section like this. This is the lever arm. Actually, this is the total effective depth up to this point at the centroid of the steels like this, and this comes from the calculations x bar as k factor times xu, some k factor times xu there, where k is 0.416, 0.416. We calculate this lever arm as this d minus kxu. Same, I have written d minus 0.416 xu. Plugging on the values that we have 0.362, our FCK is 20 megapascal. We have B as 300 mm. We have XU, this XU we have to use 315.4 mm multiplied by D is effective depth is 550 mm minus 0.416 into 315.4 mm. When we do the calculations out, this comes out to be 286.6 into 10 power 6 Newton mm. In the previous lecture, I have given you the conversions of 10 power 6 Newton mm is 1 kilonewton meter. Now we have to report this value. For example, you are designing, you are a designer, and you have given the analysis of this section. You will not report it as some decimal value. You will round it off to look like it as a some acceptable value to 87 kilonewton per meter. Kilonewton meter. This is our MUR. So we completed this analysis problem of a section which was having depth of the neutral axis greater than the axiom max. So coming to our next problem. Next problem, we will see the analysis of the flanger section. In the week 3, you would have also gone through this analysis of the flanger sections. Now, analysis of the flange sections is same as the analysis of the rectangular sections, but here we have some additional components like the flange here. Its web section is same as the rectangular section, but we have the flange section additional to it. So here we get the three cases in the analysis of the flanged sections. We get cases. Case first is if our this case first if our depth of the neutral axis or is such a small that it is xu is less than df. These are the standard symbols. Df is the depth of the flange. If the depth of the neutral axis is less than the depth of the flange, then we consider it as an equivalent this concrete section. Above the neutral axis and below will be same as AST will take the tension part, and XU above the XU it will take the compression part, and the analysis will be done in the same manner as done for a singly reinforced rectangular section. This case is simple. You would have already seen in the videos. But case second is we have second case. Now this depth of the neutral axis xu comes out of the flange. It comes out of the flange, like here. This is the depth of the neutral xu. It has come out of the flange. Here xu it has come out of the flange. So we have to analyze it in a different way. I will give you one thing. Why not if we do one trick? For example, we have T section like this. Now our depth of neutral axis comes like this way, like xu comes outside. Now can we split this T section like this? We can split it like the whole. It is the whole section from this. If I this is this section, this rectangular section. We can do the analysis for this rectangular section easily because we already had done the problem for this. And these two, let me draw with different colors. These two, smaller components. Can we do their analysis easily? Yes. They are only concrete sections. We can do easily for this also. This is, for example, this was BW, and this was whole flange of width BF. So we got a rectangular section of width BW, effective depth. Sorry, actually I have to show the effective depth only up to the centroid of the steel, up to the centroid of the steel of effective depth D. Now look, from BF we have subtracted BW, so we got both these sections as BF minus BW. So we have two things. We have uh, web section, web section of BW, comma D depth, and we have plane section, plane section of now total width BF minus BW cross. It is DF here, cross depth of the plane. Now here comes another scenario where it's okay. Now the depth of the neutral axis is greater than the depth of the flange, but we remember that the strain block given stress block given by the IS code is like this. It is having some rectangular part like this, and after that it turns to a parabolic part like this. It is up to x2 like this. X2, it's shown here, x2, up to this x2, and 3 by 7, and it is 4 by 7 x2. It has a value of 0.447 FCK. Here I can show it is 0.447 FCK, and this 3 by 7 XU. A rectangular part, this rectangular part 3 by 7. 3 by 7, 3 by 7 XU, and remaining part is 4 by 7, because their addition will give should give up a total XU. Now here comes the case is whether this 3 by 7 our depth of the flange DF. If the depth of the flange DF is less than 3 by 7 XU, we can see it from here. If I draw the T section like here, it is continuous from this side to the blue point. If I extend it like from different colors, if I extend it like this, here it is uniformly stressed. Our T section will be uniformly stressed with a stress of 0.447 FCK. This condition arises when DF is less than 3 by 7 XU, and in that we have no problem in analyzing this flange section, as it has a uniform stress of 0.447 FCK and a depth of DF. We can easily get the stresses in the flange section. But problem comes is, for example, if this XU depth is such that we get our 3 by 7 XU value as less, we have to make another one. Our 3 by 7, now our stress block turns like this. This is only uniformly stressed up to this point, and after that it is parabolic variation. And we have our DF same T section. It's here. We can see that This same 3 by 7 XU. Now the case comes if 3 by 7 neutral axis depth, it is obviously outside the plane, but this value 3 by 7 XU is such that it is less than df. It means that some parabolic part also enters into this flange section, and this section is already uniformly stressed, this little bit of flange section, but this also having a parabolic variation. We don't have a uniform stress here of 0.447 fck. For that, code gives a recommendation that code says that instead of using df, don't use df, use an effective flange width yf. That I have written the formula here. Use effective flange width YF as 0.15 XU plus 0.65 DF. Only if our XU is 3 by 7 XU is less than DF. Okay, when we rearrange this, we will get XU by DF is less than 7 by 3. It will be written in the code like this: XU by DF less than 7 by 3. But you will be already aware how, from where this condition came. It is actually 3 by 7 of XU is less than DF from this condition. Should be clearly differentiated between the two things. Code says that if it is this DF is less than 3 by 7 XU, you can easily use the whole flange depth. That is, reducer depth is equal to whole flange df only when x by df is greater than. Here you can rearrange that xu is greater than on the three. It will be rearranged like this: df is less than 3 by 7. So from this, I told you you can calculate for the web as you can consider it as a rectangular section of width BW, and XU will be the depth at the neutral axis. You can get the compression force in the web as CUW as 0.362 FCK BW XU, and MUW will be the same CUW multiplied by the lever arm D minus 0.42 XU, the same as we did for the rectangular section. And there is a condition you can use reduced depth of the neutral axis like this. After getting the decision whether you have to use this part or this part, you will be able to calculate the compression force in the flange as 0.447 FCK. We would have used whole flange, but I already told you I have deducted the web part from it. BF minus BW times the reduced depth YF. And MUF, similarly, the moments in that part will be CUF times the lever arm, D minus YF by 2. YF by 2. Okay. Now, neutral axis location will be again calculated from the equilibrium equation. C compression force is equated against tension force C. Now our C is a part of two components, one component from the web part and one component from the flange part. CUW plus CUF is equal to FST times AST. When we plug in all the values of CUF, this value, and CUW this value, we will get and solve it for XU, we will get this big formula for XU. You don't have to remember this formula. You can derive it in 2 minutes if you remember all the analysis how to do this. We have to only use this equilibrium principles. Compression is equal to tension. Equate this compression equal to tension. You can get the XU as this. This is valid for XU greater than dA. Moment of resistance will be now. Moment of resistance both will be contributed from the web portion as well as flange portion. For the web portion, we have to write it for the rectangular section, and for flange portion, we have to write it for the effective depth YF. Reduced depth, sorry, YF. We can write 0.362 FCK BWXU D minus 0.416 XU, same as the rectangular section. And for here we have used the uniform stress of 0.447 FCK of the stress block times the width will be BF minus BW, because BW we have deducted, YF is the reduced depth of the flange, D minus YF by 2. Here, D minus YF by 2. So it will be here, you have to consider it now in this case. Code says you don't have to consider it as DF, you have to consider it as YF. So our tensile force will be lying here somewhere, and it is total D. You have to deduct this part. Code says that this is YF total. You have to deduct YF by 2. So lever arm comes out to be, this was total D. This is up to the centroid of the steer. D, D minus YF by 2. Same, it is written here. D minus YF by 2 as lever arm. Same limiting moment of resistance will be when the depth of the neutral axis will be equal to the XU max. Substituting all the values, we can get MU limiting. So the problem for this question will be analysis. We have to do analyze this T section having a effective flange width BFS 850 mm, 100 mm as DF, and 520 mm as effective depth. So we have to assume first we have to assume our this XU depth of the neutral axis XU is less or equal to depth of the flange. That is the our neutral axis is lying inside the flange, as I already told. And one more assumption is we assuming that XU is less than XU max. XU is less than XU max. So I already told that when we assume that XU is less than depth of the neutral axis, we can consider we can use the concept of the singly reinforced section, singly reinforced rectangular section. So we only for this assumption we have to equate Cu is equal to Tu. Same. Cu is equal to Tu. Xu will be equal to 0.87 Fy AST divided by 0.36 FCK B. Now here B, it will be the whole B, BF, because we are considering as a singly reinforced rectangular section. When we plug in all the values, we get the value XU as 130.6 mm. Look, now compare this 130.6 mm with actual DF. It is clearly greater than DF. So the assumption we already made is wrong. This assumption. So we were thinking that neutral axis will be lying somewhere here. So this was totally wrong. It was proved from this formula. So uh, now, considering XU as greater than DF, we will not get the depth of the neutral axis. Now we have to consider depth of the neutral axis obviously outside the flange. So we will consider now, this was first assumption. Now we will consider XU greater than DF. XU is greater than DF. I told you when XU is greater than DF, for example, our XU lies here. This was our XU1 assumption. This is now XU2 assumption. So when it lies outside the flange section, we have to split it into two. One is the full web section, and these are the small flange portions. For the web section, I gave you the formula CUW. You have to compression force in CUW web 0.362 FCK BW into XU. We will calculate it in terms of the XU as substituting all the values, we will get 1810 XU. Keep in mind it is the unit of Newton here. Now we are assuming another assumption that XU is greater than 7 by 3 df, or we can say that if we convert it in a simpler meaning, df, the flange with flange depth is less than 3 by 7 xu. I already told you what it means. Flange is uniformly stressed. So we can use a uniform stress of 0.447 FCK. So compression force in flange CUF will be 0.447. This is another assumption inside this assumption. XU is greater than DF. 0.447 FCK BF minus BW of DF. when we plug all the values, here we get CUF as 536,400 Newton. So uh, we assumed already assumed that XU is less than XU max. We will have FST as 0.87 Fy for XU less than XU max. These are all assumptions we are right now making. So from this we can calculate TU as 0.87 Fy AST. Substituting all the values of AST is here. AST is 3695 mm square. We will get TU as 803,662 newtons. This is all in Newton. Applying the force equilibrium condition, we will get CUW plus TUF is equal to TU. That I already told you. CUW plus CUF is equal to TU. This is TU. And plugging all the values, we get 1810 XU for CUW plus TU 5. This is CUF 536,400 is equal to 803,662. From this equation, we can calculate the value of XU. XU is equal to 147.7 mm. Now we got the XU. We have to check whether this XU is also satisfying this assumption or not. XU is greater than 7 by 3 df. Now let us calculate 7 by 3 df value. Df is 100. 7 by 3 of 100. This comes out to be 233.3 mm. Clearly, XU calculated is not greater than 7 by 3. Let us see. Clearly, we have XU calculate is not greater than 7 by 3 D. This is 147, this is 233. So this assumption DF XU is greater than 7 by 3 DF. If we invert this, XU greater than 7 by 3 DF assumption is like this. This is not satisfied. So we have to assume another assumption that clearly it is now clear to us now that XU uh, value is DF. It lies between these two values, 7 by 3 DF. And I already told you for this situation, code has given the use of reduced depth of the flange as YF is equal to 0.15 XU plus 0.65 DF. Now XU is still unknown to us. We can keep it like that, DF plus 65. It will be in the units of mm. Okay. So CUF, when we calculate CUF again as we have to calculate it for CUF only. This one, 0.447. 0.447 FCK BF minus BW of YF. We don't have to use DF here now. CUF comes out to be this will because YF is in terms of XU. This will come in terms of XU now. This will be 804.6 XU plus 348,660. This will be also in the units of Newton. So using the force equilibrium condition, C is equal to T, again putting CUW plus newly calculated CUF will be already equal to TU. When we put all the values like this, CUW is already calculated 1810 XU, plus we calculated the new value of CUF as 804.XU plus 348,660 is equal to tension in the steel is already calculated as 803,662. Everything is in Newton. We will get the value of XU after solving 174.0 mm. So this is the value of XU. Let us check the assumptions. Is XU less than XU max? Clearly. Clearly you can check it for FE 250, you can check it for FE 250. It will be less than XU max. And another assumption, so our assumption of using FST as 0.87 Fy is okay. Now we have assumed another so our this YF that was in terms of XU as 0.15 XU plus 65. Now we can calculate the reduced depth of the flange YFS by putting XU as 174 mm as 91.1 mm. So our YF is less than DF. Okay, we can second thing we have to calculate is moment of resistance MOR. MUR, I have given the formula for MUR here as MUR is 0.362 FCK BW XU D minus 0.416 XU 0.447 FCK BF minus BW YF times the lever RM D minus YF2. Substituting all the values here, it is 0.362 FCK is 20, FCK is 20. Do it like this. We will do it like this. CU compressive force times lever arm plus force in flange CUF times lever arm. CUW is because we don't have to do the calculations again. We already calculated CUW as 1810 times it was 1800 times XU. Wait, I will show you. It was 1810 times XU. We will substitute the same value as 1810 times XU comes out to be 174 times lever RM is D minus 0.416 XU. Effective depth is 520 minus 0.416 times 174. This comes for CUF. It is CUF is this one. CUF is 0.804 times 348660. It is 804.6 times 174 plus 348660 times D 520 minus YF by 2. YF 91.1 divided by 2. So whole will be in Newton mm. Whole calculation because everything is in Newton and mm. When we calculate this value, we will get 372.8 10 power 6 Newton mm. If we round off this to 373 kilonewton meter MUR. So our required quantity, ultimate moment of resistance is this. Ultimate. So we calculated the actual depth of the neutral axis XU and the ultimate moment of resistance MUR as like this. For we have done it for the two sections. One was for flanged section, and another problem we discussed it for the this rectangular section. We did for the rectangular section. Calculated the depth of the neutral axis and the ultimate moment of resistance. Thank you everyone for joining. That was all for today.